This is lecture 8 of Logika računalništvu, Logic in Computer Science. Last week we looked at transition systems as models of computer systems, particularly of concurrent systems, and an important part of transition systems was that the evolution of a transition system, in which it moves from state to state along transitions, is non-deterministic, so one does not know in advance which path is going to be taken, and one wants to make sure that the system being modelled enjoys various desirable properties such as safety and liveness properties, and also does not satisfy properties that you don't want it to, does not have properties that you don't want it to have. And we saw last week how linear time temporal logic, LTL for short, could be used to express such properties. And this is a technology, a mathematical technology that's really used in the development of systems. One models systems, particularly hardware, as transition systems, and one formulates properties of them using a temporal logic such as LTL, and it's an important part of the engineering process to make sure that the systems do indeed enjoy the properties that they should enjoy and don't have the properties that they're not supposed to have. And because the systems being modelled are very large, one typically has thousands and sometimes millions of states in the transition system, it would be impossible to do this by hand. So computer technology is used to ensure that systems being modelled enjoy the properties that they're supposed to enjoy. And so this technology relies on being able to algorithmically solve a particular problem, and this problem is the LTL model checking problem. So let me tell you what that problem is. I alluded to it last week. So the LTL model checking problem is an algorithmic problem, a problem for an algorithm to solve or a computer to solve. The LTL model checking problem its input consists of a number of components. We have a transition system, and in order to be able to input this to a computer, it needs to have a finite number of states, so it's a finite transition system. So of course this can be input as we say how many states they are, and we in some way encode the transition relation between, for example, numbered states. So we have a transition system as part of the input. We also give it a start state, which is a state in the transition system, and the third part of the input is an LTL formula. Phi, let's say. And what the algorithm needs to do is it needs to solve the following problem. It needs to give us as output, it's going to say either yes, so this, what it does is it checks to see if the formula phi holds in the model M from start state S. So this notation was introduced last week, and what it more specifically says is we might remember that the LTL formulas, their satisfaction relation is defined along runs through the system, or paths through the infinite paths through the system. And this relation defined in terms of the satisfaction relation, you might remember from last week, it says that this is true if the formula phi holds along every path through the transition system M, starting from the start state S. So the model checking problem checks to see if indeed the formula is true on every possible path through M that starts through the start state. Since our paths are infinite, and we also have non-deterministic branching, we don't know which way paths are going to go. It is quite astonishing that one can check on a computer whether or not this is the case and output yes, and if it is, and if it's not the case, output no. So this is otherwise. But as with most of the algorithmic problems we've looked at in this course, you don't just want a simple answer if you can get a more informative answer. So in the case that the answer is no, this means that the formula phi is not true on at least one infinite path from the start state S. It outputs yes, the algorithm outputs yes if the formula is true on all paths, and so no means it's not true, the formula is not true on at least one path. So a piece of useful information we can get here is a counterexample path along which the formula phi does not hold. So in the otherwise case, it outputs no together with a path pi through M starting at S, for which the importance of this path is that the formula phi is not satisfied along that path. The formula phi does not hold along that path. Or equivalently, the formula not phi holds on the path. Okay, so that is the LTL model checking problem. This is a really non-trivial algorithmic problem. Let me write that down. It's a non-trivial problem. Because the formula phi expresses properties of infinite behavior, because the paths are infinite, and because of non-determinism, so there are very, very many paths. In fact, it's possible for the number of paths to have to be the same cardinality, the set of paths to be the same cardinality as the set of real numbers. So there's not even a countably infinite number of paths in general. So it's really not at all obvious how to check this property in finite time. So as one of the more mathematically challenging parts of this course, what we're going to do is understand how an algorithm for this model checking problem works. And it's actually going to take us more than 1 week of lectures to do this. We'll do most of it today, but one crucial step will also be done next week. So the goal of today and next week is to understand how this problem is solved algorithmically. The solution, so, is to understand how this problem is solved. So we're going to divide it into chunks, different sections of things we're going to look at, and then we'll piece them together to solve the whole problem. So what we're going to begin with is looking at a particular mathematical tool that is used in the solution, and this is something that is of interest in its own right and occurs in various different applications in computer science. So we're going to begin with we begin by looking at an important tool that we're going to use. And this important tool is something called Büchi automata. In fact, specifically, Nondeterministic Büchi automata. And in my view, these are really very beautiful little mathematical devices that are, in one sense, rather simple, but also very powerful. So to understand what non-deterministic Büchi automata are and how they work, of course, in the end I shall give a definition. But before that, I think it's easier to see some examples, and I'll talk you through the examples, and we'll look at what they're doing. So we're going to look at example non-deterministic Büchi automata. So non-deterministic Büchi automata are shortened to NBA, and because, well, a single one would be called an automaton, so a non-deterministic Büchi automaton. A plural one is non-deterministic automata. The plural is non-deterministic Büchi automata. But if you're just using the acronym NBA, then to make it plural, you just say NBAs. Okay, so the first example I'm going to call it curly A1. So I'm going to use curly capital letters to refer to non-deterministic Büchi automata. Now, an automaton is given by a collection of states, which we write as circles, and they're connected by arrows, so it's a bit like a transition system, except the arrows are labelled. And the arrows are labelled by symbols from an alphabet. So the alphabet here is sigma 1, we use capital sigma to stand for alphabets in general. So sigma 1 is the alphabet that contains binary digits, 0 and 1. And the transitions, as I say, are labelled. So here we have a transition from this state to this state, the first state to second state labelled with 1. Here we have another transition labelled with 1. Here we have another transition labelled with 1. Let's have a transition back here, labelled with 0. And let's have from this state to itself what's really two transitions, one labelled with 0 and one labelled with 1. But I'm just going to draw one arrow to save me writing two arrows. So this means we've got a transition labelled with 0 and we've got a transition labelled with 1. And I'm going to draw an arrow into this state here. This means it's a start state. And I'm going to do one other thing. We've got a start state. We're also going to have another kind of state called accepting states or final states. So this one here is a final state. So for the final state, we draw a double circle. Now, some of you might have seen finite state automata or finite state systems, as they're called, in other courses. And this is just a Büchi automaton is just a finite state automaton. But the point of Büchi automata is that one uses them differently from ordinary finite state automata. So for those of you who have seen ordinary automata, this will be what's about to follow will be something different from what you're used to. For those of you who haven't seen finite state automata, it doesn't matter because we're going to do something different now. So the point of an automaton like this is that one runs it on a word. And with a Büchi automaton, we run it on an infinite word. So we run an GNBA on an infinite word. For example, so what's an infinite word? Well, an infinite word, we've got an alphabet, 0 and 1 in this case, and an infinite word is just an infinite sequence of symbols from the alphabet. So in this case, an infinite sequence of zeros and ones. So let's give ourselves an infinite word. So 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, say 0. It looks like there's a pattern to it, but it doesn't matter if there is or not. So, of course, I can't write the whole infinite word here. But let's just imagine that this infinite word carries on to infinity. And let's label the states here. Q0, it's almost unreadable, but Q1, Q2, and this one's Q3. So I'm calling the states Q, which is standard in automata. And how do you run an automaton on an infinite word? Well, you start at the start state, so you're in state Q0 here. And then when you're in a state, you look at the next letter in the word. So we're starting with the first letter here, which is 0. And you see, can I follow a 0 transition? And then we take it to another state. So in this case, there's only one 0 transition we can follow, and it takes us back to Q0. So we do that, and we go back to Q0. So this is what it means to run the automaton on the word. Now we have a 1, and we're at Q0, and we see that there are 2 possible transitions we could take. This is what it means that the automaton is non-deterministic. We have a choice to make here. We choose either one or the other. So we could either take the 1 transition to Q0, or we could take the 1 transition to Q1. We'll take the 1 to Q1. Now we're in Q1. Fortunately, we don't get a 0 here, otherwise we would be stuck, because now we only have a 1 transition available, but here we've got a 1. So we go along that to Q2. Now we're in Q2, we've again got to 1, we follow the 1 transition to Q3. And we follow the 0 transition to Q0. And here we again have a 0 from the 0 transition, so we need to follow the 0 transition, which takes us back to Q0. Now, at this point we have a 1, and again we could follow the 1 transition to Q0 or the 1 transition to Q1. If we followed the 1 transition to Q1, we would go Q1, Q2, Q3, at which point we would get stuck. And we tried to avoid getting stuck. So here we can't decide what to do via local knowledge. We need to actually look ahead to see what we should do on the word. Or we can just imagine that this is a non-deterministic choice that's been made for us, but let's take the good choice, which is the choice that we stay here Q0. So we had an option, but it's better for us to stay at Q0. And at this point, now we've again got a 1 transition, and again we could stay at Q0, but this time that would be bad for us. So it's better to now, what we want to do is that we take now the transition to Q1, then to Q2, then to Q3, and that allows us to come back along the 0 back to Q0. We now have a 0, we stay at Q0. We now have a 0, we stay at Q0. We now again want to try not to get stuck, so we've got lots of 1, 1, 1s here, but we see that they're going to end here. So let's stay at Q0 for 2 steps, and then at this point, when we've got the 3 steps to make until we get to the 0 that'll bring us back to Q0, we branch out to Q1, to Q2, to Q3. Now we come back to Q0, and now, well, who knows what's going to happen here? So let's just now the point is not how did we make these choices at the difficult points, but just is it possible to get a run? And indeed, so far we've managed to not get stuck. And we've got a whole infinite word here. And once you've got a run for your infinite word, let's have some green here. Once you've got a run for the infinite word, you look to see whether you visited any final states. So this is a final state. Maybe I'd like to colour the final state in green. So put the inner circle in green. And we do visit the final state Q3 here. This is a 2, it looks like a 3. Let me correct that. Well, not really correct it, but just neaten it. Here we visited Q3. Here we visited Q3 as well. So I'm just circling the states on the run that are final. And the idea of an automaton is that you run it on a word, and then because it's non-deterministic, there may be several different runs you can make. And it also might be the case that there are no runs you can make. Maybe every attempt at a run gets stuck. With this particular automaton, there's always at least one run you can make, because you can always just stay at Q0, because whichever symbol you get, 0 or 1, you can always stay at Q0. So you can actually, there's always a run for any infinite word. But what we're doing this for is we want to say that the goal of an automaton is to accept words or reject them. And so an NBA accepts. Oops, it's a bit messy. So it accepts an infinite word, an infinite word, if there exists a run for that word, and the run enjoys the property that it goes through that it goes through a final state infinitely often. So there exists a run for that word which goes through a final state infinitely often. So we can't really tell whether this word is going to be accepted or not, because, I mean, so far we've visited the final state. There's only one final state. We've Q3 here, and so far we've visited it 3 times. But if this word continued 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 without any zeros in, then we would never be able to have a run that would go through this state infinitely often, because we wouldn't be able to get to this state, as we'd never be able to get out of it. So we would have to, the only run we could have would have to stay in the state Q0. So we cannot tell from this, because we don't have the whole infinite word, we can't tell whether or not it's going to be accepted. And in general, you can't tell from a finite portion of a word whether the word's going to be accepted. But we can have a look at some words that will be accepted here. So the word, so e.g., the word which we'll write like this, 1, 1, 1, 0 to the omega. So this, I mean 1, 1, 1, 0, and then repeat. So let me just define that. That's 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, and so on. So this is accepted. Because if we have that word 1, 1, 1, 0, 1, 1, 1, 0, starting from the start state, we just go 1, 1, 1, 0, 1, 1, 1, 0. So we never use this loop here. We always go around here. And of course, we go past Q3 infinitely often in the process. Whereas the word, which we might just write 1 to the omega, so this is just 1, 1, an infinite sequence of 1s. and also 0 to the omega, which is an infinite sequence of zeros. These are not accepted. Because that, in fact, in each case, the only runs for the only run for 1 1 1 1 1, so the 1 repeated infinitely often is round this loop, because you can't go through the final state because you would need a 0 to get out. And similarly, if we had 0 infinitely often, well, we never even get out of the start state. We're forced to always stay in the start state. And we see the accepted words in this case. So for an infinite word, that's an infinite sequence of zeros and ones to be accepted, there just needs to be some run that that goes through the accepting state infinitely often. So there may be other runs that don't go through the accepting state infinitely often, or in fact there always will be, because there'll always be the run that goes around this loop, but there needs to be some run that goes through the accepting state. And we can see that in order for an infinite word to have a run that goes through the accepting state infinitely often, it must contain the substring 1 1 1 0, the subword. It must contain that subword infinitely often, because every time we go around this little loop, we have to have the subword 1 1 1 0. So we talk in general about the language of an automaton, which is the set of infinite words the automaton accepts. So the language or let's say the omega language, because it's that one calls it the omega language to emphasize the omega here stands for the infinity of countable infinity, and the point is that these infinite words are called omega words, and this is a language of omega words. That is a language of infinite words of the automaton curly A1 is. So we write the language of an automaton is written as L, the omega language is written L sub omega of the automaton A1, and it is the set in this case is the set of this is a W. We should distinguish between W and omega. So it's a set of all words, this here belonging to 0 1 to the omega. Let's write that more neatly. So here we have omega. So this is just a way of saying this 0 1 to the omega here means the set of infinite sequences of zeros and ones. So this is just saying we're considering the set of those infinite words, that is those infinite sequences of zeros and ones that satisfy a property. So let's write here. The set of infinite sequences of zeros and ones. And it consists of those words that, so W contains infinitely many substrings substrings of the form 1, 1, 1, 0. Okay, so that took quite a long time to get through this first example. Let's be a bit quicker with the second example. So let's call the second example curly A2. And curly A2 is actually going to be a smaller example. So we're going to again have the automaton is given by states, given by circles. We have transition relations between them, which are labelled by the alphabet. So again, our alphabet in this case is 0, 1. Here we're going to have a loop back to this state that's labelled with 1. Let's put the label a bit closer to the arrow. And here again we're going to have, like we did last time, we're going to have two transitions here, but I'm going to write them as 1. So 1 for 0 and 1 for 1. And I'm going to make just this state here accepting. So let's think about what infinite words of zeros and ones this automaton can accept. So to accept an infinite word, there has to exist some infinite run of the automaton along the word that goes through the final state, which is the green circled state, infinitely often. So notice with this automaton, once we get into the final state, then if we want to follow an infinite word, that word has to continue as 1, 1, 1, 1, 1. So it's quite clear that this automaton will accept an infinite word if and only if that infinite word from some point onwards becomes just 1. So you get to some point, and from that point on you only see a 1, because only in that case will we be able to get into the final state and stay in the final and keep moving. We have to keep on following the word. We have to have a run. We have to be able to run the automaton along the word. If we move to this state and we after that see a 0, then we get stuck, and so that's not a correct run of the automaton. So another way of saying it is that the language of this automaton, so let's go to black. So the language of infinite words, so the omega language of A2 is the set of, again, all W, that's all infinite words, so all W belonging to the set of all infinite words, 0, 1 to the omega. And it's those W that from some point onwards are only 1. Or another way of saying that is that the symbol 0 appears only finitely often in W. So W contains only finitely many zeros. And let's look at a rather simple third example as well. So the third example, A3, curly A3. So I'm going to make it like the second example. I'll put 0, 1 here. Have a 1 transition here. We're going to go to a final state here. So it's very like the third example. Sorry, it's very like the second example, except we do not have the self loop on the final state. So let's see how this could accept an infinite word. Well, to accept an infinite word, we'll have to have a 1 somewhere in the word, which will take us into which we allow us to go into the final state. But the problem is then whatever happens, we get stuck. If we get a 0, we can't move. If we get a 1, we can't move. So if we ever try to go into the final state, we get stuck. So the only way we can run this automaton on a word is to stay in the loop at the start, and that does not contain an empty. That does not contain a final state in it, because we're just on the initial state, and the initial state is not one of these distinguished final states. So basically, this automaton accepts no words. So no word has an accepting run. No omega word, but no infinite word. We're only at the point of Büchi automata. What distinguishes them from ordinary finite state automata, for those of you who have studied them, is that Büchi automata are about omega words, infinite words, rather than finite words. So another way of saying that is that, let's give ourselves a bit more space. Oops. Another way of saying that is that the language, the omega language of A3 is the empty set. So not an interesting language, but it made a little bit, reinforced the point about getting stuck. Okay, so having looked at the examples, let me give you then the definition. And it's one of these definitions that just involves rather a lot of components. So definition, a non-deterministic Büchi automaton non-deterministic Büchi automaton over an alphabet So an alphabet is just a finite set of symbols, sigma. And a non-deterministic Büchi automaton, well, it's like the pictures we've seen above, but in order to specify that mathematically, we need to define all the components of it. So we give ourselves a set of states Q, a non-empty set of initial states, I, or actually we might even allow it to be empty, a transition relation delta, and a set of final states F. So just to write that down, just to clarify, so Q is a finite set, and we call the things in Q states. I is just a subset of Q. So this is a set of initial states. In the previous examples, we only had one initial state, but in general, you can have any number of initial states. And although I said non-empty earlier, we can allow it to be zero. Just if there are zero initial states, we can allow an empty set of initial states. But if you have an empty set of initial states, there won't be any runs. So you always accept you always recognize the empty language. So I is the set of initial states. Delta is the transition relation. So the transition relation, every transition is an arrow that takes us from one state to another state and is labeled with a letter of the alphabet. So we can view the transitions as being specified by a set of triples, a set of 3 tuples comprising of the source state of the transition, the starting state of the transition. So this one here, for this transition, we have the start state here, the label, which comes from the alphabet, and the destination state of the transition. So it's a triple with 3 components: the start state, the source state, the label, and the destination state. So we can view such triples of 3 components as given by subsets of the set product set given by the set of states, the alphabet giving us the label. So this gives us the start state, this gives us the label, and this gives us the destination state. So this is a set of transitions. And finally, the set of final states. So again, the examples above only had one finite state. We can again allow ourselves any number of finite states. And again, if it's empty, then we're not going to have any accepting runs. A set of final states. And so that's the definition of a non-deterministic Büchi automaton, and an omega word which we might write like this: A1, A2, A3, A4, A5, etc. So this belongs to, in general, sigma to the omega, the alphabet to the omega. Is accepted by the automaton if there is a path S0 goes by A1 to S1, goes by A2 to S2. Oh, sorry, let's call these Qs. So the point is Q's, realize my A's are looking a bit like Q's now. So A3, A1, A2, A3, this goes by A4 to Q4. So if we can form a path like this in the delta relation, such that, firstly, the path starts in an initial state, so Q0 is in I, and secondly, the path goes through a final state infinitely often. So for infinitely many I, we have that the ith element for it, for infinitely many indices I, we have that the ith state in the path is indeed a final state. So Qi belongs to the final state F for infinitely many I. So this is exactly saying if there exists an accepting run. That means the same thing, but I'm going to write exists rather than there is, just to emphasize that there may be many runs of the automaton on the word, and all that you need to have is that one of the runs enjoys the property that it obviously starts at an initial state and it goes through a final state infinitely often. Okay, so that's almost it with ordinary non-deterministic Büchi automata. I just want to state one more little proposition, which is a simple one more little fact about Büchi automata, which is going to be a mathematical proposition about them, which is a simple little fact, but it's actually very important because it turns out that this fact is the one that it is in the end the fact that is used in order to do model checking in LTL. So model checking in LTL gets reduced to a rather simple fact, which I'm now going to write what this fact is. So the fact is this as a proposition. And this proposition characterizes when the language of a Büchi automaton is not empty. So here we had our third example, which had an empty language. And here we had our first two examples, here and here, that didn't have empty languages. And in this first example, which the language was non-empty, well, it's non-empty because to show it's non-empty, we just need to find some word that's accepted by the automaton. And basically to do that, you start in the start state. You need to find your way to a loop that contains a final state. Here we don't even need to do anything to get to the loop. We can just see here's a loop that contains a final state. And so as long as we get the right sequence of symbols from our alphabet to keep on going around that loop, we're going to accept some word. So this language is non-empty because we have a loop that contains a final state. Again, the second one here is also non-empty. This time we need to move to the loop, which is here. So we need to do a 1. Then we move to the loop and we keep on going around it. And once again, it's a non-empty. The language is non-empty because we can take a 1 and then follow it with infinitely many ones. We can keep on going around this loop and stay in a final state. Whereas the third example, there are no loops that contain final states. So we have a loop here, but it doesn't contain a final state, so there's no way of going through a final state infinitely often. In principle, we could have a loop that contains a final state and also still not be able to accept a word, because there might be no path from an initial state to a state in the loop that contains the final state. So if the proposition needs to deal with that case, we're going to characterize when the set of words is non-empty. So let A be a non-deterministic Büchi automaton, an NBA. That should be an NBA. So then the language of omega words of A, so the language of the infinite words accepted by the automaton A, is non-empty if and only if, IFF for if and only if, there exists a path in A of the form Q0. Doesn't matter what the labels are, because whatever they are, we can just use those labels to QK. And the point is we here get to some loop. It could just be, I'm not being very precise here, but this could just be a single transition loop, but the point is we've got some loop from QK back to itself, where the path has to start in an initial state, and it needs to go through a final state infinitely often, so that means there needs to be some final state in the loop, so QK is a final state. Of course, one of the other states could be a final state, but in which case it doesn't matter if we would then make that state the QK. We still have a finite path that takes us to it, and we still have the loop going round. It doesn't matter that some state appears in two different places in our diagram. We still essentially have a diagram of this form. And for those of you who've ever watched Wild West movies from America, or cowboy movies as you might know them, so cowboys like to get their cattle using things called lassos, which are these lengths of rope that have a long bit of rope and then have a loop at the end that goes over the cattle's head. So this picture looks a bit like a lasso, so it's called a lasso, which lasso, although you pronounce it lasso, is spelt in English A-L-A-S-S-O. So anyway, so for a non-deterministic Büchi automaton, the language is non-empty if and only if there is a lasso in the automaton that starts at a starting state and which the loop goes through. The loop contains a final state. As I say, it's a simple result. You can see for yourselves that it's true. But it's a simple result, but nonetheless, this result is quite crucial to the LTL model checking algorithm. Okay, so those are non-deterministic Büchi automata. Before leaving the subject, though, I'm afraid I have to tell you that actually for model checking LTL, we don't use directly non-deterministic Büchi automata, but we use some generalization of them called, in fact, generalized non-deterministic Büchi automata. So for the last part of this lecture, I'm going to tell you what a generalized non-deterministic Büchi automaton is, and then we'll have the lecture break. So we'll do it with generalized non-deterministic Büchi automata. I'm going to do it the other way around and give you the definition first and then give you the example. And because we've already done the Büchi, the ordinary non-deterministic Büchi automata, we can go quite quickly here. So a generalized non-deterministic Büchi automata, or in general GNBA, is, so again, it's given by a set of states, a set of initial states, a transition relation, all as before, but the only difference now is that we have a family of sets of final states. So instead of one set of final states, we have k different sets of final states for some natural number k, where each set fj is again a set of states. And we can have here that k is greater than or equal to 1. And so because we've got now more than one set of final states, we're going to change the definition of when a word is accepted. So that's already the definition. And an omega word let me just make my notation consistent with what I wrote before. A1, an omega word, A1, A2, A3, A4, A5, and so on, is accepted if there exists, again, a run as before. So Q0 goes by A1 to Q1, which goes by A2 to Q2, which goes by A3 to Q3, and so on. With again Q0 is an initial state, but now the run needs to enjoy the property that for each of the k different sets of accepting states, the run goes through an accepting state from that set infinitely often. So Q0 is in I, and also now for each j with 1 less than equal to j less than equal to k. So each j indexing one of the sets of accepting states, we have, it holds that infinitely many qi belong to Fj. Well, let's make that a bit clearer. So for each j, it holds that Qi belongs to Fj for infinitely many j. Sorry, for infinitely many I. That's right. Okay, so it's not such a hard generalization. Maybe I should have given you the example before giving the definition, because it actually would have probably made it clearer. So anyway, let's do the example now. So an example GNBA is going to be the example A4. So again, I'm going to have one start state, and which is here, and I'm just going to have three states here. So this one and this one, and the alphabet in this case is going to be, this time we're going to have 0, 1, and 2. Or actually, let's make it little a, little b, and little c, just to emphasize that alphabets can consist of symbols or letters. Even alphabets normally consist of letters. And the way this is going to be designed is that every time we get an A, whatever state we're in, we go to this state here. So here we go. So if we're in the starting state and we get an A, we go back to the starting state. If we're here, we get an A, we go to the starting state. And if we're here and we get an A, and we go to the starting state. And similarly, whenever we get to B, we're going to go to this state. So if we're here and we get to B, we go to this state. If we're at the B state, we stay in the B, and we get to B, we stay in the B state. And if we're at the third state down at the bottom right here, and we get to B, we also go to the B state. And perhaps unsurprisingly now, if we get to C, we'll go to the third state, which we'll call the C state. So if we're in the starting state and we get to C, we go to the C state. If we're in the B state and we get to C, we go to the C state. And if we're in the C state itself and we get to C, we stay in the C state. Okay, so very sort of simple, deterministic, in this case, automaton, where whichever state we're in, whatever symbol we get, there's exactly one transition we can follow using that symbol. But the point is now we're going to make this a generalized non-deterministic Büchi automaton. So we're going to have two different collections of accepting states. So we're going to have the green accepting state, collection of accepting states, which is going to be one, which is going to be the B state. And let's choose a colour. So I'm going to have the purple accepting state. So the C state is a purple accepting state. So we have here K is 2. There are two different families of accepting states. Two different sets of accepting states. F1 is the accepting state. Well, let's maybe name our states. So this is Q0, this is Q1, and this state is Q2. So the states, three states are Q0, Q1, and Q2. F1 is then just the set of containing Q1. that's that accepting state, and F2 is just the set of F2 accepting states, final states is just Q2. Okay, so we've used different colours to emphasise that. So F1 was green, whoops. F1 was green, and F2 was purple. So that's just to say, so we're using the green notation to mark the states here. Okay, but the interesting thing is to look at the language accepted by this. So a word will be accepted, an infinite word, an omega word will be accepted if it has a run that needs to visit each of these two sets of accepting states infinitely often. So it needs to go through Q1 infinitely often and Q2 infinitely often. And in order for an infinite word to go through Q, in this case it's perfectly deterministic. That's not important really, but because we can also have generalized, really non-deterministic, generalized non-deterministic Büchi automata, of course. But in this case it's perfectly deterministic, and for it to go through Q1 infinitely often and to go through Q2 infinitely often, it means the word needs to contain infinitely many B's and infinitely many C's. So the language of A4 is those words belonging to those set of words, infinite words over the alphabet. So that's infinite words over the alphabet ABC. This is again an omega rather than, let me make my omega more distinct from my W again. So it's the set of those infinite words such that W contains infinitely many A's, sorry, not infinitely many A's, infinitely many B's, and infinitely many C's. Okay, so those are generalized non-deterministic Büchi automata, and I think that's quite a lot for this first half of the lecture, so that's a good pausing point. So we shall take a lecture break now, and we shall resume shortly. Okay, bye for now.